This conference will now be recorded.
All right, welcome to the ESIP and USGS CDI IT&I webinar series. This week we have a presentation from Mike Johnson, a PhD candidate from UC Santa Barbara, who's going to talk about this project, the Urban Flooding Open Knowledge Network. I've been involved in this project kind of from its inception at proposal stage, just kind of engaging with the PIs and helping to get things going. And then I attended the first workshop that they had, and it's a really exciting project. They're doing a lot of stakeholder engagement and really bringing the knowledge network kind of tech to a set of constituencies and a kind of set of data where it hasn't been yet. And so for those of you who've been tuning into these webinars over the last little while, you'll know we've been hearing about things like distributed global grid systems, or discrete global grid systems, I guess. The LOCI, the Location Index Project from Australia, some other linked data topics, and this is kind of a continuation of that. And one of the things we talked about at the latest ESIP meeting in a breakout related to some of these topics was how to cross this divide between linked data that's ostensibly about places or features on the landscape and data sets that are coverages or grids. And the discrete global grid system is one kind of take on that, where you can identify a particular cell of the discrete global grid. And there are plenty of other alternatives using web APIs and such. And so this open knowledge network for urban flooding project touches on that, in that flood models tend to be coverages that describe where flooding may occur on the landscape. But what people are really interested in with flooding is how deep is the flooding going to be at the place I'm interested in, and making those connections to, say, publish warnings or create visualizations of where the flooding might occur that's important, is the problem that the project is trying to take on. So that's the intro. I'm really excited to hear what Mike has to talk about and has to show us. So I will turn it over to you, Mike. Thanks for being willing to do this on short notice.
Yeah, thanks, Dave, and thanks for having me. So this is a project that has a large group of people working behind it. Adam and Dave are both one of them. So I think we're going to try to present a bit of some of the lessons that we've learned from the stakeholder interviews we've had, but also show what we've done as far as the content and data implementations as we transition into making this more linked data. Let's see. So the overall goal that we have is to better support water information services with a particular respect to flooding in urban systems. We're not trying to tackle any and every water resource problem within this infrastructure, but we identify that there's definitely a need within the current ability to ask questions and get answers about flooding in urban contexts. And so we are really kind of situating what we're trying to do within three main ideas that have been kind of proposed or achieved over the last 3 decades. One of them being the World Wide Web and its current evolution to Web 3.0, or the semantic web, in which data and different documents can be connected either in a linear fashion through hyperlinks, or they can be semantically linked to better understand the relationship links between different things. The second idea that we're really kind of piggybacking on is the idea of digital Earth, which was an Al Gore, Michael Goodchild idea. And that really is talking about this interactive 3D archive of scientific and cultural data that people can explore and zoom in. Google Earth is a possible realization of a digital Earth, as is Bing's 3D version of digital Earth. But a couple key points that they made in a working group in 2008 of kind of the next generation is that there should be no centralized digital Earth. There should be distributed and connected infrastructures. And it needs to be built in open data that can kind of be either global or in continental in coverage. And then the third is the national water model, which was, I think, started in 2016, was the first operational beginnings of this. And what it does is it's producing hourly streamflow forecasts for the entire CONUS. And so the connection of this temporal dynamic database, the GIS investments and infrastructure that we have, and the World Wide Web, or the connection of data, is really what we're trying to target. And we all interact with knowledge graphs of some sort. I think you guys in this group will know more about this than I do, but Yelp and Bing and Waze, Google Maps, Alexa, all of these things are about trying to connect different data to each other when asked the question to a web service of some sort of, is there flooding near me? Where is flooding? Coffee shops near me is a good example. When we type coffee shops near me in a search engine, we get a result that's temporally and spatially scoped, meaning we get coffee shops that are open and are also close enough that we can get to them. The problem is if we try something like this with flooding, we don't get the same results. If we put into Bing Maps here, flooding, the first thing it gets is to search the web for flooding. And so this shows that there's kind of this hyperlink relationship rather than kind of get the contextual idea of what is flooding in the context of a locality. So when we click on that hyperlink there and go to search the web for flooding, we see something like this, that there is a very generic what is flood based on Wikipedia. We see on the right side there, kind of tucked off the back, that other things that are somewhat related are drought and tsunamis. But there's nothing really specific about flooding where this query was made, which was in Santa Barbara, California. There is an ad for a flood insurance provider in California, but it's pretty generic in all contexts. So if we extend that a bit and ask for, okay, flooding near me instead, see that we get a global flood map, we get USGS flood information, a flood warning system, and again, we get that ad for low-cost alternative to FEMA. But we see that there's nothing really contextualized about flooding for the specific place where it was made. And the only kind of semi-reasonable top entry that we see is an advertisement, and again, it's the same advertisement that we got for flooding as a generic versus flooding near me. If we try Google instead of Bing and we again search for that flooding near me, we can again see that the results that are given are kind of not spatially or temporally scoped. The first one is just where can I find flood maps. The second and third one are Australian specific. It's kind of an interesting site, but it's for Australia only. And then we see in the videos and the content that's presented there, it's neither spatially nor temporally scoped to Santa Barbara or the time which it was made, which was on January 28th. And we see instead that the videos are for massive floods in central Texas and the Midwest and in these 4 states back in 2017 and 2018. So this idea that there's not quite yet a semantically linked way that we can marry space and time with respect to hydrology and flooding through the internet is kind of what we're trying to tackle. So we want to be able to, at the end of the day, same way that people Google for weather or other conditions near them, provide hydrology in a service in some way that they can have a better understanding about their historical and current floods conditions. And so to do that, we are going to focus just a bit on this one catchment that's in Breckser County, Texas. And I'm going to go through this particular catchment as kind of an example of how we're going to build the content or the data around kind of building or realizing these semantic relationships. So it's kind of an idea of Texas. For those who aren't familiar, San Antonio sits in Breckser County, and we're going to focus on this one catchment here that's within the NHD. Now, one thing that is very nice about the NHD is it somewhat conforms to this high feature standard of a catchment or a holistic entity that can be realized in multiple different ways. So when we think of this catchment, we have the area boundary that we see here, which kind of contains the topography information. So here we're seeing the elevation as a DEM. A catchment can also be realized as the flow line that drains that catchment, or the flow path. And it can also be realized as the outlet, which is where all the water from that particular catchment drains. And so we can kind of capitalize on how different agencies and different entities have can place themselves within these different realizations of a catchment as we're looking forward to build hydrology and its connections with urban systems. So in the context of the outlet, just as kind of a background here, the way that we're going to convert stream flow from the national water model that's given at each of these points to depths is with a synthetic grading curve. And so if there's questions at the end, we can go into a little bit more detail with this. But essentially, this is taking the terrain information to create floodplain cross sections. And from those floodplain cross sections, determine a relationship between how fast water is flowing through the channel and ultimately how high that water is going to pond. We see here in panel B that it's using this hand raster. Hand stands for height above nearest drainage. So instead of relating elevation to a continent-wide datum, it's relating it to a datum that's specific to the individual reach. So it's the height above that flow path that we saw, and it's specific to each individual catchment. So we went back to that breakdown of Rexer County and had all those catchments. Each catchment has been rectified to its particular lowest order by the flow path. And so when we see this, we see from this realization that we have an outlet, and at that outlet we have a power law exponent and coefficient. Those are the power law relations that give us that synthetic grading curve we see here. So from that exponent and coefficient, we can take a flow and convert it to a depth. We also have an area of the catchment that we can use for things like how many buildings are within this area. And we also have the stream flow path itself, which gives us something about length. So this is kind of the context of the hydrology that we're situating ourselves within. This is the data architecture that defines CONUS-wide hydrology as we understand it. Overlaying that hydrology understanding is this kind of urban multiplex, these different urban systems. And in this case here, we're showing that there's OpenStreetMap buildings, there's OpenStreetMap roads. Those small little orange dots are bridges from the National Bridge Inventory. And there's many other ones that the Department of Homeland Security has substations and power lines. Texas, the state itself, has a list of Superfund sites and dams, things like this. So there's a lot of open public data that defines kind of this urban multiplex is what we're calling it. And what we need to do is figure out a way to connect this hydrology understanding, this idea of how water flows on the landscape and how stream flows relate to water depths, to this built environment. And so if we take a cross section here, we zoom into that southernmost part of this catchment, we take a cross section across here, we can see that along the elevation, and this is quite exaggerated just to show what we have. But we see that the blue points are roads, places where roads intersect this transect. Green are buildings, and here we have this bridge, which is defined by the vertical clearance in the data set. And we also have this building that sits up high on the top here. And so the idea is that if we have stream flow and we have an elevation data set, we can ultimately say, okay, how high above a stream are each of these points? And so no longer is it recognized solely as a building or a road, but it's identified as a point above the nearest drainage. And from that, we can define that at different levels of stream flow, there's going to be different depths of water. And as those different depths of water kind of encroach in the landscape, there's going to be different risk points that are impacted. So at a stage right now of 6 meters, we see that there's some amount of buildings impacted, there's some amount of roads impacted, and there's a bridge impacted at some point. And so at each of these different stage levels for each of these different flows, we have a different total tabulation of how many impacted features there are along this transect. So the idea of the impact node is how we are thinking to kind of triplify or make this data kind of linked. It's the connection between the urban multiplex as we know it, and it's the connection between hydrology, which breaks apart a landscape and relates to that National Water Model Flow database. So within each particular risk point, or those points that we saw along the transect, each risk point sits within an NHD catchment. So that gives it the catchment and the hydrology that it sits within, and that has a specific value. It also has a feature type. In this case, looking at this red one, it's an OpenStreetMap building. And within the OpenStreetMap database, it has an ID itself, which we're calling 111. So in total, we see that the ID of this particular risk point or this particular impact node is the concatenation of the COM ID and the native data set, in this case, OpenStreetMap ID. And for each of these points, there's a critical depth, which is that elevation that we saw in which flooding will occur at that point. And then it also has a relation within just a generic spatial reference system. So every point then is situated both in an X, Y, and Z, and in its relation to the NHD, which is the National Hydrography Data Set, if I didn't clarify that at the beginning, and its situation within, in this case, the OpenStreetMap building infrastructure. And so this way, these impact nodes are now spatial features which kind of connect these two different data sets. The challenge is then how do you take buildings and roads and these different spatial features that have different representations and abstract them out to an individual risk point or an individual node. And so this is just kind of a schematic of how we are anticipating doing this. And so we kind of process this by catchment by catchment, and polygons are defined by their lowest point within the coverage of their individual polygon. Polylines are defined, their critical point of that area where we're most concerned about flooding is defined by their lowest elevation along the transect of the entire road through the catchment, and the points are very easy. They're extracted based on their location. And so the underlying data set that we're looking at is this 10-meter NED, National Elevation Data Set, or HAN data set. And the points that we overlay it can be anything that someone has represented as a geospatial feature. Doesn't matter what their representation is. The methods have been generalized in a way that we can extract what we're calling the impact node or the risk point for that individual feature. At this point, then a risk point or an impact node is defined by the location of its XYZ in the overall reference system. Its Z being that critical depth value, and the COM ID that places it within the appropriate catchment, and it gives it a way to index to the national water model flows. And so we go ultimately from something like this, where we have kind of this overlay of this urban multiplex or this urban system over a hydrologic feature, and we were able to convert it into something like this. And so for this particular catchment here, we can see the points. These are open address risk points. They're bridges from the national bridge inventory. They're dams from the national inventory of dams. There's the open street map. There's the Superfund sites that Texas makes public, as well as their public water supply wells. So everything that goes into this is open public data that can be crawled and connected to another database outside of it. But in total for Brexer County, that one that we saw, we have edging up towards almost 2 million impact points that we can use to forecast flood depths at any particular time. And in doing this, we say that there's a particular COM ID, and for that COM ID that relates to a stream flow forecast from the National Water Model. And at any time, if that stream flow forecast converted to a depth through that power law relation floods one of these points, we know which points are impacted. And we can ask questions like, how many bridges are impacted? How many roads are impacted? How should we maybe change our routing navigation apps based on impacted roads? So this becomes a queryable data set of impacts, not impacts of particular feature types. So the ultimate idea that we have with this impact node is that we have these things that are static in time and don't really move. And these are open public data sets that really are this GIS investment, digital earth, if you will, representation of what we know about space and in the human built environment. On this other side, we have these hydrologic models. It can be the National Water Model in hand. It can be an ICPR model. It can be any hydraulic or hydrologic model of interest. As long as that model can convert something to water depth, it can be intersected with this critical depth. And instead of forecasting flood inundation maps, we can start forecasting flood inundation points. One of the things that we've been working pretty closely on is that we don't want to be reliant on any one model. Just like Digital Earth said, it's got to be this open and interconnected architecture of multiple infrastructures. We want to be able to do the same. So we can ingest hydrologic simulations from any model, and that way we're going to be model agnostic. And really it becomes about aligning specific points in time, so those individual risk nodes, within a hydrologic location of the particular model. And that location has to be defined by the model grid. And so in the case that we just saw, it's clear that it's that height above nearest drainage point that we try to get, and that's really defining that XYZ location. And as long as that the data is accessible online, so it can be linked and water depths can be produced for a model, it can connect within this. And so to show kind of an example, we've been working specifically with two different models. The first one being the water model in hand, which we just talked about, and the other one being ICPR, which I forgot to change that one. But in all respective purposes, these are two totally different models. The water model is a regular 10-meter grid, has a geographic coordinate system, its units are in meters, has a course detail, the national coverage course being that 10-meter grid. It has no 2D hydraulics in the way that it performs over wind flow or things like that, but it is free. It requires no in-house knowledge to use, and it does predict stream flow. So stream flow has to be converted to depth, and it's to be done through the synthetic rating curves. ICPR, on the other hand, is an irregular triangular mesh, has a projected coordinate system, its units are in feet, and it has really high detail, but is only able to run on small areas. So like in this case, it's a very high resolution model set up around Houston over the time of Harvey. It does include 2D hydraulics, so it gives better representations of how water flows on the surface, but it's private, it costs money to parameterize and run, and it predicts water surface, not stream flow or depth, but a water surface elevation that needs to be converted to depth. So I made a note about how hand was, we were defining a hydrologic location by the X, Y, and Z within this regular grid. Within ICPR, they have to be done with more of a triangulation process. So for each risk point, it has 3 closest IPCR nodes. So when we look at this triangular mesh, we're able to identify what are the 3 closest nodes, what are those distances to those nodes, and based on those, how do we interpolate a surface? And right now we're just doing inverse distance weighting procedure. But the idea is that a core attribute of each individual risk point is a hydrologic location, and you can have one or more hydrologic locations. So any one point can have its situation within the hand and national water model grid, and it can have a location within an ICPR grid if there's that model running there. And so in this way, any model of local infrastructure that people have invested in or already run or are comfortable with, you can add these different hydrological contexts to an individual risk node point to give you some level of model agreement, some level of model certainty. People can work with what they're familiar with. But as long as a water depth can be produced and this location can be rectified to these risk points, then there's a connection between things like OpenStreetMaps and the water surface wells and these depths that are being produced. We're also interested in how do we ingest other information. So if somebody in Houston, Texas has this really nice information or database about their infrastructure that they want to share or make active within this, how do they share that? And so within this, they just need a way of rectifying it. So we're going to show one example that we made a population knowledge graph based on the set of NHD catchments near Houston, Texas. And we produced a couple different metrics for each one. So we took census data and took the aerial weighting of different measures like total population, populations older than 75, population younger than 25. We counted how many OpenStreetMap buildings were in each catchment, and we tabulated different land cover rasters, so how much of each of these catchments is low density urban, high density urban, medium density urban, and all of this information can be stored then in the same way. So this is an external graph that through this common feature ID, which is the same as the COM ID in the NHD, it's been linked and allows us to ask questions such as, if a flow rate of X is occurring in this catchment, how many substations might be impacted? How many people do we expect to be at risk? How many buildings are in this area? How much of the urban area here is dense? So we can start linking questions between these outside data sets, such as population and land cover, to the hydrology and to the urban multiplex, and people can connect information of their own interest to these risk points. So I think that's kind of the broad introduction that I wanted to share. And we'll go into a couple of the prototypes that we've been building out around this. And so we're doing it with R and R Shiny. But the idea with this is that once the graph is out there, really it can be hit. It will be API accessible. It can be queried with Sparkle. But people can use it in ways that they want to. So this is just one manifestation of how this knowledge graph can be kind of put into action. So the area that we're going to look at is this area around Houston, and the time period that we're going to look at is Hurricane Harvey. That way we can show something of interest, and we're not going to show no conditions, which we would if we didn't take a historic event. Within this area that we just saw, kind of surrounding the city, these are the data sets that we're using. So we have OpenStreetMap roads, OpenStreetMap buildings. The Texas Water Board provides open address points. Since this has been changed over to open address, so the address points that we see here can be accessed for anywhere in the country as well. The Texas Water Quality Board provides Superfund sites and water wells. The National Bridge Database provides bridges, and so on and so forth through these. You'll see that each one has different geospatial representation. So some are polylines, polygons, NetCDFs, rasters, so these different coverages that Dave was talking about at the beginning. These risk points and this way of doing this allows us to rectify these different types of geospatial representations. In total here, we see that this area also has close to 2 million risk points within it. And in total, using all this data, if you were to just use it in ArcMap or QGIS in a typical kind of let's build a flood map and intersect it, you'd need to process over close to 14 gigabytes of data. So not only is it machine intensive, but it takes a lot of processing time in each step. The formats are also quite varied. Another strength of this knowledge graph or impact point approach we're taking is it rectifies these 8 different unique formats across different scales, and it condenses it down to something that is about 2% in total space. And so then just one more broad high level before we start seeing some of the applications of this is we have from the National Water Model, each hour, there's a forecast put out for X amount of hours out. So you might have a stream flow for now, a stream flow for 1 hour now, 2 hours out, 3 hours out. This is what we're saying from those big ideas at the beginning. This is what's really kind of enabling this. We have these GIS investments. So over here we have the COM IDs, right? So this is the NHD that has specific power law coefficients and exponents stored with areas and lengths. we have any graph that any individual or any group builds out. So in this case, we're looking at that population graph. And then here we have all the information we have in these open data sets. So in this case, for the building class, we see that something is it comes from OpenStreetMap. It's a residential class. A lot of OpenStreetMap features are tied to DBpedia, allowing you to kind of chase this semantic link even farther down. And we have these impact points, which is what allows us to connect all of this together. So from this, we see that we have a COM ID and a point 101 or 111. Because it's ID 111, we know that's residential and it's come from OpenStreetMap. Because it sits within COM ID 101, we know the power law relationship that gives us a synthetic rating curve. We know the total area and length, so we have access to those different high feature representations of this catchment. We know something about the populations that are within this catchment because somebody's populated this other graph. And we have access to a real-time time series of streamflow forecasts through that COM ID. So this COM ID and this class ID within OpenStreetMap can be used to relate many different features that otherwise aren't so easy to bring together. So through all of our talks with these different groups, and we've had two major workshops, one in Houston and one in Raleigh, where people from kind of the Southeast have come together, people that are county managers, floodplain managers, private engineering firms have come together to tell us what are their pain points, what are the things that they're invested in. And through a lot of work on people on the urban flood team, they've been kind of consolidated into these 4 use cases. The first one's Paula. She's a planner with a general interest in how our area is changing. So she lives in Houston, is just generally concerned about what's happened in the past and what might happen in the future. Pete is tasked with maintaining and aggregating information about the power grid of Houston. So he works for the power companies. Erica leads the first response effort. She's kind of your fire chief, police chief, who's interested in real time what's going on. And Susan's interested in kind of the long-term effects of stormwater planning or identifying places of risk and who might be at risk if certain things happen. Important things to note about the demonstrations that are coming up is that even though we're using Harvey as a case study, all the information is currently hosted as if it's real time. So this would be the same, what you're seeing for Harvey historically would be the same thing that you would see for a real-time event moving forward. Other than the graph, there's no pre-computation, so everything that you're seeing is done on the fly. It's pulling data in, it's creating these risk points, it's identifying where impact's happening, and there's been no speed up in the videos that you're being shown. That was a question that came up at a couple of the workshops of is this working in this way? So starting with Paula, she's an urban planner and she's kind of interested. She's online and she's looking at downtown Houston. She sees that, oh, Harvey just happened and yet we're investing $9 billion in public and private investments. Is this a good idea? What are the historic conditions that we've seen at specific points? And so she sees this nice map and she Googles flooding near me. Now this is kind of just a demonstration of, instead of flooding near me, which we saw at the beginning, which had no spatial temporal scope, because there's now information, semantic links between flooding to the hydrologic events near me gives you space and time. You're able to access things for web surfaces like the 3 representations of hydrology based on the high feature specification. So you can see, oh, there's my location. I'm sitting within this NHD catchment. There's my nearest reach. And there's no flooding predicted near downtown Houston today. So you can get some sort of information based on the risk points in that area. You can see the weather because now there's an understanding that flooding is kind of this weather-related natural systems process, and you can see that there's graphs with the national water model showing the purpose or the current forecasts. Because it's spatially scoped as well, the videos are more in line with who she is and where she is when she's asking this question. She clicks on this first link here at Get Flood Info. The question she's asking really is the area that's growing experience in amplified hydrology. So to answer her question, she can start zooming into the area that she's interested in. And so this is for planning and future purposes, and it really allows people to see what has happened in the past. So she identifies that specific building that they're saying is going under construction, is planned to be renovated. She can find it, it quickly identifies her, it does the reverse geocoding, it pulls up the entire archive of the national water model. So this is a 23-year hourly forecast, and it's able to show her not only what does that forecast look like, but for the bankful exceedances based on those rating curves, what is happening to the hydrology. And on that right plot we saw there, which unfortunately passed, you saw that there was an amplification in the signal of flooding events in this particular area. And so this is just something that is available for CONUS now. You can look at it anywhere. You can see your points. You can see based on the current reach, what is the amplified signal. And that was at a 2-year reoccurrence event, but we've also built in the 100-year and 500-year, and we're still figuring out the best way to communicate risk there. So on the back end of what we just saw, when somebody goes into the Shiny app, the first thing that's done is the USGeo server is used to identify what COM ID they're near. So that is actually intersecting with this national coverage of these NHD catchments. So it identifies the COM ID. The OpenStreetMap geocoder is used to reverse the lat long, and that's able to say, okay, we're at this particular address. The map click is used to index a hand value from a HydroShare resource. So it's a OpenDAP threads accessible raster service. So it gives you that particular height above nearest drainage for that particular point that was clicked on. And the entire national water model reanalysis product is pulled from a local resource now, but there's already funding and a path forward for putting that data set out on the web. So 5 different data resources, 5 different locations, all of these taking up massive disk space in their own, was facilitated through this graph-based logic and the web services that it's able to access through being able to rectify someone's space within their local hydrology and within the question that they're asking. The next one that we'd like to show is Powerful Pete. So he's this utility operator charged with kind of maintaining systems or the power system within this Houston area. Something he might be interested in saying, okay, so flood alerts for Houston, how do I get information for when flooding is going to come? Again, because flooding can be spatially and temporally scoped, and alerts for Houston can also be given a place and time. You can again see, okay, well, we're in a certain place. This is where you're looking at. Weather is related. Flood alerts are these certain things, but we'll also see that there is this architecture built around alerts within this knowledge graph system that we're hoping to build. And what might happen with this is if you want to get customized alerts for the substations that he oversees, you can go to this page. He'll put in, oh, my name's Pete. It's Powerful Pete, so his email is powerful@gmail.com. And he's particularly interested in particular subsets of points. So he's interested in substations. He's interested for an area. So all those map tools on the left there, you can click particular points if you're interested in an address point, or you can search this particular or a whole area. You can be interested in flood and depths of certain points. And so he's interested in any of these flood stations that he's just identified reach a critical value greater than 2. So if anything is flooding to a level 2 feet or more, he's going to get an alert based on these points. And so as Pete's sitting on his computer one day during Harvey, an email comes through because there's an expected event to be happening at one of the risk points that he identified. So somewhere in the knowledge graph, when these new forecasts are read in from the National Water Model, these points got triggered as being potentially at risk because the value of, or the depth that's being forecasted was greater than the depth of the impact node. And so with this, then he can go in, open up a web interface that's particularly geared towards power and energy. So if we change the date to the 12th, which is where the predicted forecast is supposed to happen, we see that each of these points represents a substation, and the area surrounding it is the area that that particular substation serves. So we were told by P&L that these in polygon around particular substations is a good representation of the total area served by that station. So in these, we see each red point is the one that is predicted to be flooded at the time that he asked for. So September 12th at midnight and 6 hours forward. So 6 hours forward of midnight, how many stations are going to impact based on the forecast? And as he clicks around and zooms around, you can see go to different points, select that one. It gives on the left here the particular water depth of the predicted forecast. You can bump it out instead of looking only 6 hours into the future, look 24 hours in the future, and see that September 12th around 6 p.m. there's expected decrease in total water depth. Now here we can also see the link to those population information that we saw. So based on what he's queried here by clicking show me the details about this power station, there's an intersection between the area served by that and the population graph that we have tied to the NHD catchments, and you're able to get information such as what's the population served by this particular area, how much of it is high density, how much of it's medium density, how much of it's open space, and how many total buildings are contained within this area. So all this geospatial processing is being done on the fly based on the question. So right now questions are done in a click and point kind of way, but eventually we hope to build it out to a more natural language processed sort of way of doing this. But that's in the future. So far we've seen people that are interested in historic information. That was Proactive Paula looking at what's happened here in the past. Pete's looking at the time during the hurricane, what's happening now. what does the forecast look like? You can use this forecast slider to see X amount of hours out from the current, and you can click on different substation areas and see whether if they were to go down, if this risk was actually to manifest, what are the forecasted impacts in the intersection of kind of the hydrology in the urban system. So then on the ground in the time of these impacts, you have Pete who's in the office trying to help plan resources, but you have people that are out in the field. These are the emergency responders that are tasked with distributing resources, figuring out where to station personnel and machinery, things like that. And so this is personified kind of by Erica in our example. So Erica would also search for flooding near me. Now, when she makes the request, she's out in the field. She knows there's flooding. And so flooding near me, instead of seeing no flooding as we had before, now there's a specific warning. There is flooding predicted near Houston starting at 6 a.m. and it's projected until 4. So that's a cumulative request on all of the risk points within what's defined as Houston's area. And it's understanding that there are impacted nodes within that system. By getting near me, it's able to kind of query a lat long, can show information about the water depths in your area compared to a general human form. How deep are those water, with the red and yellow signifying the depth levels that NOAA has said are dangerous and extremely dangerous. You can also start to see some precipitation grids taken from web feature services. I think this one's taken from NextRad, and so that's just calls based on your area, a particular view to look at. And we'll see from this floodgetinfo.com. This is a domain where we hope to host all of these things. There's emergency guidance, road closures, available shelters. And these are triggered based on the fact that there is flooding. So the fact that there is flooding gives it a temporal scope to looking from right now in the future, rather than if there's no flooding, it's looking from right now into the past. And so Erica's questions are kind of, what do neighborhoods look like? What are on the ground depths? What Superfund sites will be impacted? What will the next few hours hold in terms of particular flood movement? And so when she goes into a response page, just quickly to generate things as we go, you go to the September 12th, you look for a particular hour. So on September 12th at 6 a.m., what do we expect to see? And on the fly, it's querying all the data, it's generating the risk points, and it's showing what is expected to be impacted. You can filter based on what types you're looking at, and you can get total tabulations of what's impacted within the Houston area. So at this point, we kind of had 16,000 OpenStreetMap buildings that were impacted, 1,000 bridges, 28 dams, 2 airports. We're all expected in one way or another to be impacted by this flood wave that was coming. You can symbolize things in different ways, and you can zoom in and really get an idea of how dense these points are in different areas. So this is a neighborhood that is expected to be impacted. Somebody wanted to look at that particular impact point. What's the forecasted water depth in relation to some form? You'll see that it crosses that threshold for extreme risk. Just based on filtering types, you can click substations and recenter your map. You'll see where the substations are. Each one again gives you information about the water depth, what the ID is in its native data set. And you can also look for Superfund sites. And so the Superfund site looking kind of takes us into our next example, which is focused on stormwater and preventative. Oh, one last thing is if you're looking at the rainfall, you can bring in those NextRad images. So this is kind of sketchy because it's bringing in the current NextRad information, overlaying a historic event, but the idea that you can read in your current rainfall forecasts is something that we're very much interested in. One of the groups on our team is really working on improving precipitation forcings through combinations with different radar assimilations. And so if that becomes a success, we can then be showing precipitation forecasts that are downscaled and give a little more information to these people that have really made it clear that they want to see water on the ground and where water is typically falling. Our last persona is stormwater Susan, and she's more of a planner for catastrophe. So she's what happens if something goes wrong. And so she might be able to search for Superfund water quality in Houston. And again, because Superfund water quality in Houston are all semantically scoped to a space and time, within the context of hydrology, she can get a map of Superfund sites. These are these particular impact nodes that have been tagged as a Superfund. Because Superfund is an entity in Wikipedia, you would get a certain knowledge page over there on the right, and you get more relevant information. And with this one, she would be looking for failure checks. So she's particularly interested in Superfund site failures. And so if we zoom in and she selects one, and this is a groundwater water plume. What happens and what are the downstream impacts of what's going on? So by clicking on that and waiting just a bit, it will on the fly generate all of the address points and homes that are downstream of that particular impact point. It'll color code them by the distance from the Superfund site itself. It'll tabulate how many are within that range, and it'll draw convex holes around those impacted points so that you get kind of area representations and point-by-point information of what are the potential impacts if something was to go wrong at that Superfund site, or what are the downstream contaminant potentials. And so in all of these cases, everyone that we talked to, the biggest thing that they wanted was kind of this information that we've shown, but more than anything, they want flood maps, and they want to be able to see on the fly interactive graphics of where is floodwaters and where is it predicted. And that's been a real pain point for people to be able to go from simulation to a raster into a web map in a performant way that is also fast enough to be of any use. So one of the real advantages of these impact points that we have is that by using things like address points and buildings and road networks, these points are incredibly dense. And by being incredibly dense and being able to identify very quickly how fast or what the water level is at each of these points, we're going to show here kind of from start to finish. We loaded up, we launched the Shiny app, we already set it to this date, but as it's thinking right now, it's generating all these things, it's finding the impacted points, it's generating a raster of them, it's putting that raster into a slipping map, and then it's generating the map. And so on the fly, you can start generating things like this from the density of these impact nodes, truly kind of perform an interactive web tiles that people can interact with and really answer what it is that they're after. And so these are all impact points that have been addressed somewhere within our knowledge graph, and the color that you're seeing is representative of the water depth, or the amount that's above that critical depth value. And you can change different dates, and those rasters change, and they update only the nodes and places in the raster that have changes. In that case, there wasn't a ton of change, but we can see in this area here there was just a bit, and you can get down kind of the street and home level of what some of these predicted disasters are going to be. And so the big take-home point that I think we would really like to emphasize is that while all of the prototypes and the interfaces and those things are really nice, what's really I think the core of the project that we're doing is the content that's within this knowledge graph and how it's linked to these different open data sets. We do want to, as we talk to more people, in the same way that Google Maps kind of gives you these pre-canned restaurants, coffee shops, and hotels, that's what most people want. Those are the big actions that Google Maps serves. We want to find what those are for this urban flooding as well. Do people want flood maps? Do they want to see impacted points? Do they just want to see address points? Or what are the key things that everybody wants to see? Simplify that into kind of these major issues, but then open everything up so that people can build out their own applications, contribute their own data, and really kind of get better answers that have space and time embedded in them about flood events, especially in the urban interface. And so with that, that's what I've got. Thank you very much for listening from the whole urban flooding team. Particular acknowledgements are to the team, Adam and Dave, who are here, tremendous players within this realm, UCSB Geography for supporting this for me personally, the NOAA National Water Center for putting up the model that makes a lot of this possible, 3 cohorts of Summer Institute participants, which has helped me, and then NCAR, UT Austin, and Dr. Maidman's group, and then all of the interviewees that kind of gave us the right direction. I think we all had an idea of what might be nice, but I think we're much more confident after these interview sessions that the directions we're pursuing are ones that are meaningful to people that might use this system in the end. And so with that, thank you very much.
Awesome. Thank you, Mike. That was a tour de force. Really impressive. And so you have one question in the chat about the digital elevation model that this is all kind of based on for generating elevation of your impact points.
Yeah. So the impact points, this goes back to the attribute that we're calling hydrologic location. And so if it's grounded within the national water model and the hand approach, then it's based on the 10-meter national elevation data set, and that's what hand has been computed over. In the ICPR grid, which is that other model in the Houston area that we're working with, they have a much finer, I believe it's based on LiDAR. So they actually have LiDAR at all the nodes in that triangular mesh, and we're interpolating the ground the ground elevation for all of our risk coins from those 3 nodes, as well as the water surface elevation. So long answer short is that the elevation model really depends on the hydrologic model that we're interfacing with. Does that answer the question?
Oh, yes, thank you. I do have another question.
Yeah.
Because you have huge amount of data being used in the system. I'm wondering, like, normally we don't have clean data for this application. And how do you do the data auditing?
Are you talking more data handling or assessing for data quality?
Yeah, assessing accuracy of data. And if you have any errors in the data, definitely if you send out a warning message, you have the errors in those messages. How do you filter out those errors?
And so that's currently, I guess there's 2 potential error sources. There's errors in the geospatial data sets like OpenStreetMaps and the bridge data sets, things like that. I don't think we are going to try to target errors in those. I think we're going to say if they're part of these authoritative global data sets, we're going to take them as what they are. And when somebody looks at it, if they see there's something wrong with the position of the point, they can make their own judgment call. On the issues of errors within the hydrologic forecasts, that is something that we've talked about and we don't have a perfectly straightforward answer yet. One thing we're working right now is to kind of bring in the USGS National Water Information System, the string gauge system, bring that into this as well, which we're almost there. And that'll be able to give a close kind of approximate of, is this area performing well, so we can give some statistics on the closest gauges and how well they're matching the forecast from the National Water Model. And as we get more models in here, we're hoping that the combination of models, like in the Houston area, we have both the ICPR and the National Water Model running. In some ways, we're hoping that by reporting multiple models, it's a crude ensemble approach to dealing with some of that. If there's something really bad going wrong in one of the models, you'll have the other ones telling you something else. And so then it becomes a user call.
Thank you.
I unmuted I muted a few phone users, so everybody should have complete control over their mute at this point if anybody has other questions.
I just tried to pose a question in that we're working on this next generation observing system where we could have, for example, hundreds of temperature sensors or soil moisture, real-time storm surge, maybe even real-time high water marks with or storm sewer overflows, with the sort of the binary, on off, like water rope detection.
Yeah.
Could that all feed in? I guess it could feed into the National Weather Service, but could it also feed in so that you could actually adjust this synthetic rating curve and things like that?
100%, yes. I don't think we would want to in the system adjust the synthetic rating curve, but outside of it, yes, 100%. And I could also, sensor networks are something we've been working with or talking with Texas. They have this extensive sensor network of string gauges that do velocity and depth on their bridges, and we've been looking at ways on how do you bring sensor data into this to not only kind of correct things, but also show a different type of view, kind of back to that data quality issue. I think if you have sensor networks, I think that's something we'd be very excited to see how it could tie in with all this.
Okay, so maybe I could communicate with you about that.
Yeah, that would be awesome.
David, I
worse than-
definitely, yeah,
Okay.
yeah, I definitely see tremendous promise for a number of applications on this project within USGS and NGWAS. Event-based response and registration, kind of short-term network, I guess is the term we use for it, is one of the really cool ones, I think, because we have this practice of when we see a big storm coming, we get out on the landscape and throw a bunch of sensors out, and with cell phone telemetry, that becomes a real-time telemetered network potentially, and adding that to this graph would be really cool. But so David, there's I'll get you on the invite to, or maybe you're already on it, an invite to a further follow-up session with USGS in particular in a few weeks.
That would be great. Yeah, and I'll send you an email and put me in contact. Right now we're installing this test site in Philadelphia, and I'm just looking, sort of like where to send the data. Part of it is the green grass cameras, but also I was looking at InfluxDB. So just, anywhere we could send this data,
Yep.
Kind of looking for a place to send it to. Okay, thanks.
Yeah, that if it's out there on the web, I think that would. Context to this project as a whole is it's a weird NSF project in that it's a 9-month phase 1 for 40 teams who are doing knowledge network things, not flooding related, and then phase 2 cuts that down to I think about 10, and that's a 2-year advancement. But part of the proposal for phase 2 is partners and new things that can be engaged with by this project. I think a sensor network like what you're talking about would be really advantageous to put within this, both to get your data out there, but also for us to play with how do you engage sensors or this Internet of Things or all these different things that are potential data sources for urban flooding. So that'd be really exciting.
Okay, great.
So the one thing I wanted to ask is if you could go into a little more detail in the last few minutes that we have on your kind of fully integrated grid view of the graph that shows kind of all the impacted points. Can you talk just a little bit about what's behind the scenes on that? Like how there's a lot of information summarized in that one graphic, and I'm just wondering like what all comes together to generate that view.
Which one?
I'm talking the kind of like the landscape is on fire, like that you had on your title slide.
Yes. Okay. Yes. So yes. Okay. So this is that Houston area. So we knew the NHD catchments within it, and that also would be a quick query. I mean, NHD Plus tool, some of the things you've worked on just to see the server in general, you can quickly get what COM IDs are you interested in. And from those COM IDs, then we can query either. So this is coming from a combination of the ICPR and the National Water Model. And so we pull time series, the forecasted values for this hour for those COM IDs. Well, for those COM IDs from the National Water Model and from all risk points in the IPCR grid. And from that, based on either the interpolation from the ICPR points or the synthetic rating curves, we generate a depth at every risk point or impact node. From that, then those risk points, those are stored as individual values as a matrix. I don't know how far into the tooling you want to go. Those are then passed as a matrix to the stars package, which is an R utility and R package used. That stars raster is then filled. So it takes a 3x3 kernel around everything and only fills in cells if 5 of the neighboring 8 cells are of a flooding value. So that helps clean up a lot of the speckled. It's a similar kind of kernel method you might do in NV or ArcGIS. And then from that filtered raster is passed to leaflet and put on top of the map just as a stars object.
Okay.
Super Does that answer your question?
Yeah, totally. It's a fantastic visualization of the overall picture. That's really cool.
Yeah, and I think, and Dave, I'd really like to talk to my advisor here. So there's still some speckled speckling, as you can see, especially kind of in the, like in the reservoir where I guess it doesn't matter, but that's a very prominent issue, that Lake Houston up here.
Yeah.
What's the right balance between a visual that looks right without overfilling? Because as you process more and more and fill in these speckles, you inherently have to grow the bounds of the edge effects along like the stream channels and things like that. So for our last workshop, this was the happy medium that we'd come to, but I think still cleaning this up, both in the speckles of flooding and not flooding, is something we got to work on.
Interesting. All right. Well, we're just about at our hour. That was a really great talk. Thank you so much.
Yeah, well, thanks for listening, everyone.
So yeah, this has been recorded. We'll get this up on YouTube. I'll send a reminder of its availability out to the list. If anybody has ideas for future talks kind of in this vein or moving in different directions, please let me know. I've got a few ideas of things that I will be setting up, and I'll be in touch on the list about what's coming. But with that, thanks for coming, everybody. And we've got, oh, great. Yeah. All right. Great talk, chat. Thank you very much. We'll see you.